Get the okay. So we're going to open up that initial SIR model. It's called initial SIRS version 1. It's posted to the Canvas site, people finding it. Okay, I think it's kind of down there in the main page. Okay. And it looks like this. It's susceptible, infected, and Republican. Does anyone remember the dynamics associated? When we ran this model with the default assumptions, note that this lacks the waning of immunity transition we later added or flow. What's the dynamics of this? What's the characteristic dynamics of this with the default parameters? Anyone? When I run this, what do I see in terms of, say, number of infectious people? Not. There's no waning of immunity. Good. That's a key component. So that's going to have a big impact on its dynamics. And in a sense, it does balance itself out, but it balances itself up around, okay, this is going to be really tough. Ethan?
Yes.
Okay.
The infective dose spikes up and then drops kind of slowly to 0.
That's right. And so there is a balance. It balances around 0. Why does it go to 0? There's people yes,
there's basically less people than there is capability of infection. So essentially it starts to run out of material to burn and
exactly. Yeah. There's no fresh wood for the fire. There's no fuel for the fire. That's because the fire depends, that generates infectives. What does it consume? Susceptible. Susceptibles are needed to keep the infection going. And as susceptibles get depleted, it limits the efficiency and ultimately the existence of people being able to still be infected. So let's remind ourselves with that if we could. Oh, there's a nice pendant here. Nice, I guess it's an earring. Looks like with an Ashland hand axe type design. So anyone missing an earring? Okay, you know it's here. If you it's a nice sort of purplish color, sort of. Okay, so we're running it and infectives are the magenta color here in the middle, and it rises and then it falls. Now, why is it rising very quickly at first? Yes, yeah.
yeah, more people are there to get a contact with you.
Yeah. Okay, so there's lots of people for contact. Let's favor this side. Oh no. Okay. So here we have infectives, right? I'm describing this model at a somewhat higher level, but infectives lead to what? Yes, and I shouldn't say that. Yes, Mr. Deshaun.
I was just gonna say, like, the reason is dryness in the beginning.
Yes.
Is because we have like a lot of infectives, but as we progress,
Yeah.
they spend time in recovery, which reduces the amount of infectives.
Well, yes, it's true that they undergo recovery, absolutely. We do have something like this, where infectives lead to new infections, and the more new infections lead to more or fewer infectives. New infections lead to fewer infectives? Yeah, more. Yeah. And as I said over there, with some simple assumptions, but for the nature you very commonly get out in exponential growth. One person infects 2, infects 4, infects 8. Yeah, you comfortable with that, Patrick? Well, what happens as this goes on? New infections depend on something else beyond infectives. It takes 2 to tango. What's that? Susceptible. Yeah. So, let's get this camera somehow. Capture some element of that. Okay, so we have susceptibles. Oh, so susceptibles. Right? Mhm. Okay, and the more susceptibles, does that tend to lead to more new infections or fewer new infections? More, in fact. Lots of fuel, lots more infections, right? You're surrounded by susceptibles more. You got lots of infected, right? So there's a plus arrow here, but what's sort of close the loop, finish the loop? I'd say there's a loop involving susceptible. And it's a key loop. Yes, name? Justin, thank you. Exactly. And this is a what loop? Negative. And that balances that out, right? You get that depletion. For those not seeing where these causal loop diagram are extracted from, where's the positive feedback here? Tell me where the positive feedback is here. Involving infectives and new infections.
Bottom left, the second arrow really drawn, but it's
Okay.
it's a leak infection.
Okay, yeah, so it sort of goes around this way, right? Involving these things, more infectives, greater infection prevalence, more force of infection and more new infections, etc. So high level here, if you were to increase this, it would increase this, increase this, increase this, and round and round she goes. Yeah. Where's the balancing feedback here? Find me the balancing feedback. Find the homomorphism. Okay. Yeah, where is it? Yeah, susceptible to new infections, and new infections, the higher the value of new infections, it does what? Lower susceptible. So the trouble, if we have more susceptibles, it increases new infections. Yeah, that's that part. But having the more new infections drain susceptible becomes lower than it would otherwise have been. That doesn't mean it's going, well, in this case, it is going down, but doesn't always mean, but it's lower than it would have been. So I'm saying this causal loop diagram is implicit in the stock and flow diagram if you know where to look. Are we comfortable with that? This causal loop diagram abstracts that portion of the model. Yeah? Okay, now let's ask, okay, so we've seen the dynamics there. What if we were to double the number of contacts people have per day? What do you think would happen?
I think that's part of going fast, so it'll basically shift to that.
Good. Yeah. That.
Well, I was gonna say, essentially, you're increasing it at a more rapid rate at the start.
That's right.
It'll still go down.
Good. Yeah, so it'll go up faster. And it'll take less time to, or will it take more time or less time to turn around? Less time. It'll turn around sooner, right? Will its eventual value be different, the number of infected? No. So what I did is I right-clicked on this. I did copy. I pasted in from the top, and I'm going to call this double
doubled contact. Oop, doubled contacts. Okay, are we okay with that? And let's change that parameter. So in the scenarios, we specified parameters, and here we go. We're going to change mean contacts per day from 20 to 40. We okay with that? Notice it's bolded to mean that it's no longer the default value. I'm going to run it now, and Ken prognosticated that it's going to rise more quickly. And indeed, you folks said plateaued and indeed turn around sooner. Ultimately, its trajectory is going to zero. Or do we see that? Yes. So Justin. Good question. What do you think? Yeah, so let's check it out. There you go. The answer is yes. It's like 200,000 or so, or 150,000 more. It rises to a higher level. And we're going to follow that curve. It's kind of the opposite of flatten the curve. Okay. Let's suppose we were to do something that lowers the contact rate. Maybe put in place social distancing, or maybe put in place, ask people to work from home if they could, right? So let's have a halved, HALVED contacts. Instead of 40, it's 10. We okay with that? Okay. Okay, here we go. I should have asked you, what do you think happens? What's the net effect? Sorry?
But also to what's the right and the peak is not that high.
The peak is not high, indeed, it's only around 500,000, right? With Justin's observation, the doubling went up to almost 900,000. And this is just around 500,000. We've flattened the curve. We've spread it out. Now, do fewer people here become ultimately infected? I'm saying if we ran it out far enough. No. Everyone gets infected eventually. It may take, may take a long time, but everyone eventually gets it. Okay. Okay. Yes. Okay. Now, let's suppose we were to do something crazily larger. So I'm going to do, instead of doubled, I'm going to do it with 10 times larger. Okay. Here we go. So this is going to be 10 times contact rate. Okay, so instead of 20, it's 200 people per day. What do you think the effect would be there? You tell me.
Yeah, big increase in the effective reproduction rate.
Yeah.
Blasts off.
It blasts off. You can, it's almost, it goes so quickly, it's not even visible here, but you see it turning around at over 1 million people and then coming down, right? And you barely see the susceptible decrease by this time. It's only updating every 1 day, and so much has occurred in the first day, for example, 200 people per day. It's spreading like wildfire. Okay, now how do we really flatten the curve? We lower it further. Let's add 10 times smaller contact rate. Okay, so instead of 20, it'll be 2. What do we expect to see now? Let's see what the number of infectives is doing. You don't even see it in the above curve. What's going on? Yes, Pat.
It's taking a longer time to observe. Because there are less context studies.
Okay, so that would be a reasonable guess that it might be, gosh, if increasing the contact rate leads to a faster spread, lowering it, we saw with having it, it leads to slower spread. That maybe here it's just really, really slow. But is that what's going on? If you look at this graph for number of infectives, what's actually happening?
It's dying out, like the basic reproductive number is less than 1.
That is exactly it. The basic reproductive number is less than 1. One person started infected, and what's happening from there on? Is it spreading? No, they're recovering faster than it's spreading. So the number of people infected in this model, instead of merely going up at a slower rate, it's doing what? It's going down. So we've crossed, let's call it the tipping point. The behavior now is qualitatively different. There is no outbreak. Instead, there's a steady progress towards recovery. We've shifted it by changing those parameter values. We've shifted to a new mode, a new basin retraction. It's heading immediately towards it dying out, not even having the outbreak. Do you see that this is rather qualitatively different? It's not merely if we ran it far enough, everyone would be infected. Is everyone going to be infected here? No. No. You have the first person, maybe they'll infect before they recover, very small number, but basically there's no outbreak. The number of people with infection on average will be going down from the very get-go. Do you see that? Now that's what we hope for from a well-controlled system. That's what you hope for smallpox. That's what you hope for measles, right? Well, it's not true for smallpox, but for measles or for pertussis or for chickenpox, that's what you hope for. Now, falling vaccination rates have gotten in the way of it, but that's what you're aiming at is a situation where you are herd immunity or where the infection is, in other words, unable to spread effectively. It's so inefficient in spreading that it doesn't spread at all. We pushed it to a new mode. We've crossed that tipping point. Now, Ethan mentioned the key quantity, which was based in that video that I shared earlier, which is the notion of a basic reproductive number. Okay. I want to emphasize this is a reproductive number, so it's about the number of people infected by an infected before they recover. But we talked about two types of reproductive numbers. The basic one is a very special one, and the effective reproductive number. And these go by different names. This one universally goes by R0, R0. British pronunciation of 0. Effective reproductive number goes by like star or RT or RE. These are just different ways of denoting different sort of subcommunities tend to interpret it. When I say R not, the basic reproductive number is very special. What do I mean by that? Yes, Ethan.
Will give you the highest potential of susceptibles you can have.
That's it. That's it. Yes, this is what applies when you're surrounded by susceptibles. This is like a worst case situation, right? We want to be able to plan for the worst case situation. if someone's surrounded by susceptibles, maybe they're the first person in Saskatoon bringing in the illness. Flying to the airport and they start to spread it. How many people are they going to infect before they recover? And what's the key value for that where the infection will no longer take off, what we just saw? What's the key value where if it's less than it won't spread. If it's more than it will cause an outbreak. It'll rise before it comes up. One. That's the key value. Why is 1 the key value? Why not 0? Yes, no.
More or less than replacement.
Yeah, it's more or less than replacement. After all, if there's one person sick. The question is, do they even replace themselves before they get better? If not, the number is doomed to go down over time. They want to go replace themselves, and so there'll be even fewer people after that. By contrast, if the first person infects, say, 2 people, maybe those infect 2 or nearly 2, because now some people at least are not susceptible. And you get this sort of successive doubling, the successive reproductive number that leads this exponentially, right? I as the patient 0 infect 2, and those infect almost 2, and those infect almost 2, and those infect almost 2, and you have this serial interval between those generations of infection, and you might have a doubling every 5 days, or doubling every week, or something like that, and it leads that exponential growth. Do you see that? So 1, it turns into 2, turns into 4, 8, 16, 32, 64, 128, 256. 512, 1024, 2048, 4096. That's computer science. You don't, well, I think. Okay, so basic reproductive number. If it's less than 1, it doesn't take off at all. We're in a different regime. By regime, I mean the behavior is qualitatively different. Do you appreciate that? You understand that point? If it's bigger than 1, as that indicated, there'll be an outbreak. Now, it may be a slow outbreak, it may be a fast one, but there'll be an outbreak. Generally, if there's a bad contagion, like for a pathogen, you hope you're in this regime where it's contained, where its basic reproductive number is less than 1, where it will die out. If you can't achieve that, you hope for a slow spread, or at least you can spread out the number of people getting. Okay. Okay. Now, I want to turn to the other model. The model you folks built, but which I posted on the site too, for your convenience. Version 2 of this, where it lives up to the name of being an SIRS small. And what do I mean by that? Speak on, impetuous youth. Back to susceptible. That's right. Yeah. Okay. So let's go open up that model. May we? Okay. So we're going to open it. It's going to complain a little bit about opening up something with the same name, blah, blah, blah. But here it is. Okay, you tell me. Let's remind us, what's the dynamics of this? First of all, let's suppose the basic reproductive number is less than 1. Is that possible with this? Let's put that in if we can. Okay, so let's go add. So let's go add that scenario, if we may. Okay, here we go. Let's make this 10 times smaller contact right? Remember, that's what did the trick. You remember that? Okay, and this is mean contacts per day of 2. We good? What do you think you'll see?
Yes, same thing. Yeah, same thing. Why?
Because it's not limited by number, it's susceptible.
Yeah.
That's kind of thing.
That's right. That's right. And really this later machine, I mean, this model differs from the previous one, but machinery that's kind of somewhat distal, somewhat downstream of that, right? So what's going on here? It doesn't even realize this is going on essentially with it dying out. I mean, this will be of key importance in just a minute. But as far as it dying out, that's not going to be affected by this. You know, if it dies out because it never gets off the ground, the initial person recovers faster than they grow susceptible. You know, it's going to be somewhat immaterial if later they recovered would wane in terms of infection. So let's go run this. We really willing to run this? And let's see that borne out. Yes, so here we go. And let's go see the number of infectives over time. And is our anticipated, is Ethan's comment borne out? It is. Okay, it's going down. You see that? Okay. Okay, so if the basic reproductive number is less than 1, what happens? Dies out. Right? You comfortable with that idea? Now you tell me, you remind me. If you ran this with the default assumptions, what would happen? What do we see? And how does it differ from the SIR model seen earlier? Ethan is topping the leaderboard. Ethan is leading the class discussion, but I want to get some broader, and Malcolm's also been very active. Let's get someone who hasn't spoken up best.
Quick, one thing before that.
Yeah.
I think V2 is gonna be one indirect or posted,
Oh,
right? Yeah, the same.
okay, that's my bad if that's the case. So tell you what, let me go update that right away. Okay. Sorry, this is you're seeing other class material. Okay, where is my okay. Okay, well, I'll just call up a new browser and we'll be done with it. Okay, come on. Let's just get it posted. Here we go. Okay, and let's go down there and we're going to delete this one and upload another. Okay. Yeah, I think I know why that is. I think it's because I posted it with that poor choice of names before the take-home exercise, and I did a disservice to you. Here we go. Okay, and it's replace. Okay, it's there now. The correct one is there now. Thank you, Babs. That's much appreciated. Others though, what's the dynamics we'll see on? Yes, Ali.
The infection won't die out as was in the earlier case.
Yeah.
It's sustain, the number of infected will sustain a level
Excellent.
above 0.
Okay, number of infections is the same. So if there is an outbreak, it doesn't go inevitably to extinction like the previous one. Instead, it what? Yeah, it remains there. Okay. So it remains what we call endemic. Okay. And let's go check it out here. So I'm going to run it. And here we go. And we can see it. So give me a narrative of what's going on. Let's point out two things that are rather different for this graph from what we saw of the comparable graph for the SIR. Give me two things that are different, perhaps, yeah.
The successful one, vertical population, like about, like the beginning is kind of the same, but it kind of starts with the same value at the end.
They do plateau at the same value, and that's kind of interesting. It turns out that's somewhat of an accident here, but what's notable is that the susceptible is not going to what? It's not approaching zero, right? And, excuse me, yes, that's true, that's true. But what's also notable is the infectives are not going to zero, right? Right? Why are the infectives not going to zero? Well, what keeps them greater than zero as time goes on? Ken?
Since there's a loop now, the recovery can flow back into the.
Yeah, exactly.
susceptibles, which essentially gives it more fuel.
It gives more fuel. Okay, that's right. That's right. So as if the wood that's burned now suddenly becomes able to sustain fire again and it's purple. Okay. And why is the susceptible going up? Towards the end, not just going down and down. Well, same thing, right? In fact, it's the very fact that susceptible goes up that sustains the infection, right? Because the infection needs fuel to burn. Are we fair with that idea? Okay, now, what would happen if we were to double this? So double contact rate, right? Sort of a similar, remember we did that with the other model? You tell me, what's the effect going to be here? Oh my gosh. I was just thinking, the old version of any logic, it might crash at this point. There we go. Okay. Okay, well. I haven't seen that bug in a while, but okay. Okay, here's version 2, and maybe it will allow some of you folks to catch up. Here we go. So you tell me, you've been using longer. What's the effect going to be of doubling the contact rate? By the way, the key is save before you click on this. What's the effect? What's the effect going to be of doubling the contact rate? Yes.
The endemic level of infectives will remain higher than it was with the.
Good. And Jeff, you're cutting to the heart of the distinguishing feature here. Because it is true that certain things are held in common. Doubling the contact rate will do some things we also saw in the SIR model, like without the recycling of the population. What is that? It will do what? Peak. Make the peak earlier and higher. That's true. But Jeff cut to the heart of the matter about the steady state behavior, right? And he said that this is going to have the effect of elevating the infected population in steady state. Do you see that? It's gone up. How about the susceptible population? That's gone down. If fewer people are remaining susceptible. We can quantify how much of it is, relative position is quite different. Now they're not almost equal. The infectives are almost double the susceptibles. We'd have to look at, how much did one drop versus the other rise. But I would suspect if it's similar levels of recovery, we might see the loss of one being the gain of the other. Okay. So here we can get behavior that's that has changes the steady state. I want to ask here with this model, what would happen if we had a much longer time till immunity waned? Right now, I think it's 60 days. If memory serves me. So what do you think would happen? You tell me. What do you think would happen? We had a longer time until immunity waned. Yes, Malcolm.
Yeah, we trend back to that non-recycling fact. So
Mm,
depending on how much we increase it by, we might go back to that original section, but you expect them to, the population to roll over less quickly. So if the virus doesn't maintain a certain ratio to that recycling, then it'll either die out or it might.
Yeah. Yeah. Okay, so let's, good. I like the way you're thinking. If we raced it towards infinity, it would be what? If we made it super, super long, it would look a lot like what? Yeah, the SIR model, because it would be like almost no one recovering. Let's double the immunity time, but I'm gonna have to ask for your dispensation, if I may. I'm gonna need to run this for longer. So I'm gonna say run it till time 500, if we're okay with that. Because 100 is going to be too little to really see the effects well. So I just changed it to be stop time at 500. Okay. Okay, well, we see it. Oh, sorry, we need to do something else. It's a silly thing up on this graph. So what did I do? I went and I created this scenario. I changed the mean time until immunity wanes to be double its normal value from 60 to 120. And I changed its stop time to be 500. But there's something else I need to do. And it's a silly little thing of little significance for the model's assumptions. It's just a display thing. What I need to do is, I think it's under the data update area here. We need to display up to 500 latest samples. Okay. And is there something about scale too? Yes, time window 500 under scale. So we're giving us a wider window of time, a wider time horizon to display. Okay, so we've doubled it. What do we expect to see now? How might that affect things? What's new here? What's visible new here? Yes, Troy?
You know, it's like that sign where the like kind of goes up and then comes back down and then back up and back.
Yeah.
Kind of goes up really quickly, you know, I'd see it looks like it's a little wavy, but not much.
It's wavy. Yeah, it's Justin. What else do we notice? So if we compare this, mark particularly this susceptible. Note what's going on here. And I'm going to compare that and with the default one. I'd like to run this for 500 too, and I apologize, but I'm changing that, but we don't have to change because we already changed the settings for the graph, which are shared between. So I just made the baseline also run for 500. Okay. And here with the baseline, so this goes up to about 150, well, what is it? 150,000, yeah. It goes down to about 33,500. Okay. Now with this double waning time, what do you think its ultimate value is going to be? Do you have any prediction? Sorry? Yeah, there's not a lot of reason perhaps to anticipate 150,000, but it goes down to a value that is what? lower. Why is it lower? Why is it lower?
Can you imagine this get through? It takes more time for the recovered people to start putting that susceptible number back up.
Yeah, so the susceptible get depleted for long before kind of the cavalry arrives, before the new folks start getting back into susceptible. That's not a good analogy in this case. Before the new reinforcements to get sick arrive, the new folks coming in, right? You have a longer time until until susceptibles, flow in. Let's double it yet further, okay? So we'll have maybe we'll do 5 times, 5 times waning time. Okay, so instead of being 120, it'll be 300. What do you think you'll see then? So I changed it to be 300. What do you think you'll see then? Sorry? Even lower values, right? So here we go. It dips to something like 1/3 of that value for the default, right? It's like 11.8 now. And now you see this sine wave. What's going on with that sine wave? Who can comment on that? Yeah.
Basically, it's trying to balance itself out, like as you said, with the broom example, if you lean it one way, you have to kind of, or if the broom leans one way, you gotta balance it back out, so it's kind of oscillating until it reaches that.
Yeah.
state.
Yeah, that's right. It's like negative feedback with long delay associated with it, right? Or that was kind of just a happenstance diagram, but it's like we end up having a long delay associated with so new infections lead here to what? New infections deplete susceptibles. They lead to more infectives, but what else do they do? New infections, well, I'm sorry. This is not the most artful way to describe it. Infectives lead to what? What's a missing loop here? Yeah, to more infectives leads to more recoveries, right? And the more recoveries, yeah, before that was just like a sink, right? It just like went in and stuck. They just stayed there, right? But now the recoveries eventually lead to, although we might more artfully eventually say this leads to more recovered individuals, right? And then the more recovered leads to waning. And then that leads to more susceptibles. And what's going on is we're putting a long delay associated with that. Is this loop? What's the polarity of this loop? This is the plus from infectives to recoveries. The more recoveries are there more recovered individuals or fewer? More recovered individuals, more waning or less? More waning, more susceptible. So what's the net effect of this loop here through susceptibles, new infections, infectives, recoveries? It's a positive feedback, right? Which is kind of interesting. Does it lead to exponential behavior? Not really here, right? It does lead to sustaining of the infection. So it does lead to the infection leading to a buildup of people that end up sustaining it, but it's not always the case that positive feedback leads to that that exponential, but there's a delay associated with it, and you see this. And Ken described it pretty well. It's trying to get into balance, but it's getting into balance in a way that there's a delay. And so it's like overshooting, right? As Ken was saying, it's like overcompensating. It's like going too far on a icy road, where the car skids too far and then you head back and around. There's a lot of systems like this where we overcompensate. It takes a bit of time till we realize it, and we've exceeded it. So what's going on when this rises up here? The number of susceptibles rises up to 200,000. Well, you tell me. Let's talk about this this interplay here. So we have this initial rise. I think we understand this pretty well, this initial rise in number of infectives, right? And we have the draining of susceptibles. Okay, you tell me, when this is really, really low, what's the implication for the spread of infection? There's not as many susceptibles to spread the infection. And so that limits what? The amount of infection that's going on. That's right. And therefore, there's a bigger imbalance between recovery and delayed. So the number of infectives will be what? Going down, right? This is below the level where it's sustainable. Where's the level that it's sustainable? Like this, or equally the level that susceptibles are at when this is at its peak? And in both cases, they're right around here. At this point, each infective infects how many people before they recover? One, right? And what equals what at that point? Inflow equals outflow. You could see it either way, kind of at an individual level. I infect one person before I recover. At a overall level, inflow equals outflow. In terms of inflow into the infected stock equals outflow. Are we comfortable with that? That's why it's in balance. That's why it's not going up or down at this very tip peak. And that's why it's not going up or down here, right? It's in balance. This number of infectives is in balance here. It's not going up or down in any significant way. Okay, but let's keep on understanding this. Okay, so now after that point, well, you tell me, why is it drained so low? Why is the number of susceptibles drained so low? Because there are a lot of infections. Tell me, why does the number of susceptibles still drop, even though the number of infectives is coming down? After all, infectives are coming down here. Why, all in this portion, right? This portion here. Why is the number of susceptibles still going down? Why would number of susceptibles be going down if what? Why is the stock going down if outflow is greater than inflow? What's the outflow from the susceptible stock? New infection. What's the inflow of susceptible stock? Waning of immunity. Not recovery, waning of immunity. So it is true the number of infectives is going down here, but that doesn't mean that infections are stopping altogether, right? And the outflow is still greater than an inflow. There are not many people becoming susceptible. So it goes down here, and then it starts rising up. Why is it rising? Why would a stock be rising? Inflow is greater than. What's the inflow to susceptible? Waning of immunity. What's the outflow to susceptible? Okay, yeah. So the number of susceptibles is rising here. Now I've said, and you can actually check out my, is this what I want to look at? Well, it's maybe what I want to look at, but it's not what I'm supposed to look at right now. Is this? No. Okay, where's my, okay, now we're in deep trouble. Okay, where are my slides? Okay, no, that's not what I want. Okay, okay, no. Where are my goodness, where are my slides? Okay, somehow my slides have vamooshed. I was going over them before class. Here they are. They're hidden behind Canvas. I called up Canvas and it hid my slides. So folks, I want to emphasize here that this number of new people being infected, do you remember the formula? What is this formula? This is the formula. Well, what's this? If I cover S, what's this? Force of infection. What's the force of infection? The chance per unit time that a susceptible will get infected, right? Like the chance per day that I'll get infected. If it's 1%. Susceptible to get infected, right? Makes sense? So if you multiply that by susceptible, what do you get? Number of new infections occurring per day, right? 1% per day times 100 people will be about 1 per day actually getting infected, you know? Or times 1,000 people will be 10 per day, yeah, like 100. Okay, so this is the number of getting infected. I want to highlight to you that we can write it that way, and that's good, and we use that in our formulas, but we can rearrange it. After all, multiplication under the reals commutes, meaning we can move these values around, right? We could interchange S and I, right? Right, and we could write this as I times C times S over N times beta, right? Look, to tell me I can't do that, right? But just reorder it, yeah. Help me understand that. Okay, so this is the formula for the rate of new infections, right? Right? That's what this is. We agreed that's what this is. The formula giving the number of new people getting infected per unit time of 10 people per day, right? That's what this formula is. All I do is rearrange it commutatively, right? And switch the position of the I and the S. And now, on a per susceptible basis, what is this C times S over N times beta? Give me an interpretation of that. Well, that infective meets how many people per day? People per day, C. Of them, what fraction are susceptible? S over N. So C times S over N is the number of what that they meet per day? Susceptible people they meet per day. Times beta. Beta is the chance that they will transmit to each of those people, right? So I'm an infective. I mean, 100 people per day. Of them, 50% are infected, or sorry, are susceptible. So I mean 50 susceptible people per day, right? I can infect them, and each of them I have a 1% chance of infecting, right? If that's the case, right? Then I infect on average 0.5 people per day. If each of those 50 people I meet per day, 100 people overall, if 50% S over N of them are susceptible, so I meet 50 people per day. If I have a 10% chance of infecting a given one of them with that contact, then I'll infect how many people per day? If I'm meeting 50 susceptibles per day and I'm an infective, I'll infect how many? 5, yeah, 10% of 50. Do you understand that? So here, C times S over N times beta is the number of people that each infective is infecting per day, per unit time. Do you get that? Okay. I should be jumping groups. Okay, so I think you'll see for this that S over N directly throttles the number of people that are getting infected, right? If S over N is half its normal, if S over N were suddenly to go down by a factor of 2, you would have a factor of 2 smaller number of people being infected, you see? So the fraction of people susceptible, ladies and gentlemen, mark my words, susceptible is a key driver between, in terms of what's going on. So we're going to switch back to this. Here we go. So here's our plot of infection. Okay, so so I'm telling you, the number of people susceptible is really low here. And so there's very few people getting infected. And so outflow is greater than inflow for susceptibles, for infectives rather, and therefore this is continuing to drop. Do you understand that? Few people coming in, lots of people leaving from infectives, so it's going down. But it's going up here. The fraction of people who are susceptible is rising here. Why is the number of infectives still going down? Alter this period. The number of susceptibles is rising. How can infectives go down? How can the stock of infectives go down? Well, you should be able to tell me. Yes, I'm there. Okay. So the number of susceptibles is rising, and that's a reflection of the fact that what is greater than what? Inflow is greater than outflow. What's the inflow to susceptibles? Waning of immunity. So susceptibles is rising because of waning immunity. But why are infectives still dropping, even though susceptibles is rising? I've just told you susceptibles throttle the number of new infections, but number of infectives is still all through this period when susceptibles is rising. Susceptible is going up and up and up. Hey, up and up and up here, and yet the number of infectives is dropping. How could a stock drop? Outflow is greater than inflow. It's true the inflow may be going up, but if the outflow is greater than the inflow, the stock could still be going down. You get that point? Don't get caught up in this notion that just because the inflow is going up, the stock has to be going up. No. And I hope that little exercise we did about number of people in the hospital ward should be getting you to think about that, right? Just because the number of people being admitted to hospital wards is now going down doesn't mean the number of people in the hospital ward is going down. No, it could still be going up if it's greater than the outflow. Okay, so it goes up, and it's only at a certain point that it crosses a key value which allows infectives to go up. What's the key value that it crosses? When what equals what? So inflow is equal to outflow for infectives. That's why infectives is flat here. But susceptibles at that value will be such that each infective will infect how many people before they recover? One stinking person. You get that, understand? Or one unlucky, right? That's the key point where suddenly this will start to rise, right? The number of people who are infected will start to be going up. But note it overshoots. Why does it overshoot? How can it possibly overshoot? Why doesn't it just drain? Because why can a stock still be going up even though the number of new infections will likely be going up all through this period? It's still going up. Why is it going up? Because what makes a stock go up? Inflow greater than outflow. What's the inflow to susceptible? Waning of immunity. So it is true more people are getting infected during this period, but there's still more people waning immunity than there are people getting infected. So it's gone up. And it overshoots its value, as Ken said, it overshoots its value. And now it's all set for this outbreak. Do you see it? And now there's enough susceptibles to allow the infections to start to spread more efficiently. And there's this mini outbreak. And that brings down the number of susceptibles and brings up the number of infectives again until this point. Now, at this point here, what's going on? Like, at this equilibrium? Well, let's suppose at this equilibrium, I were to say, I'm going to have more infectives arise at this equilibrium. What would happen? I'd start to drain the number of susceptibles, and it would no longer be sustainable for the infection to spread. And it would pull down the number of infectives, it will come back into balance, right? Or if I were to drop the number of infectives, what would happen? There'd be a buildup of susceptibles, which would lead to more infection. Do you understand that? So it's in balance here. It's in an endemic balance. Okay, that's all we have time for today. But I hope you're getting a sense of the rather textured story that's written out in these stocks and flows. And if you come back to the basics of it, you can come back to these basic principles of effective reproductive number, how many people an infective infects before they recover, but also the basics of stocks and flows. And do not, please, do not get confused that if an inflow is going up, that means the value of the stock has to be going up. Or that if an outflow is going up, that means the stock must be coming down. It's the balance of the two. It's inflow greater than outflow. And you can have dynamics of those inflows and outflows, but as long as inflow is greater than outflow, the stock will be going up. As long as outflow is greater than inflow, it'll be going down. You get that? Okay, key principles, okay? Okay, that's all we have time for today. I'll look forward to talking briefly now, but we'll talk more tonight, 5:30 to 7. If you want to be there online, I'll be there. Thanks.